Hello everyone and welcome to another video on AVL trees. This is my part 3. If you haven't watched the part 1 and 2, I basically went over just theory in part 1, and then in part 2 I wrote code for the AVL trees. So if you haven't checked those out, make sure to check those out first before we begin with this. This is just going in a little bit further into the topic about the analysis, performance, and real-world relevance of AVL trees. So why AVL trees outperform regular BSTs? Regular binary search trees can become unbalanced, height up to order n, and AVL trees make sure there is a height balance of less than or equal to 1, ensuring order log n height. And then here is the advantages right here. Let's get to the next slide. Okay, so rotating costs and trade-offs. AVL trees rotate more often than red and black trees, which is good because extra rotations make slightly slower inserts and deletes, but faster lookups, and AVL trees are perfect for search-heavy applications. So you might wonder where AVL trees are used in real-world applications. So where are they used? So databases use AVL trees for indexing and query optimization. Compilers use AVL trees for managing symbol tables. They are also used in memory management like Linux kernel, which use AVL for virtual memory gapping, and they provide consistent lookup times, which is critical in systems that can't have delays. So how AVL trees manage data? So AVL trees manage data behind the scenes. They use two key concepts, which I'll go over in the next two slides. Those concepts are binary search tree properties and height balance properties. So first off, let's start with binary search tree properties. So in this, all nodes follow the standard rules of the BST rules. For any given nodes, all elements in its left subtree have a key that is less than the key of the node. All of the elements in the left subtree have a key that is greater than the key of the node, and this is why there is such a fast search. And now let's go to height balance tree properties. This is the defining feature of AVL trees. For every node in the tree, the height difference of the left and right subtrees must be -1, 0, or 1, 1, 2, 3 in brackets. This balance makes sure that the tree cannot skew like a linked list, which would massively reduce the efficiency and speed of the performance. So what are the advanced variants of AVL trees? So I'll also be making another video for this part, which I'm going to show you guys more of the code on these 4 different AVL trees. So first we have threaded AVL trees, we have the persistent AVL trees, the AVL plus hash hybrid trees, and cache friendly AVL trees. So as you can see, there's multiple different AVL trees that you could use, and they have different features for each one of them. So let's go with a threaded AVL tree first. So these trees combine the self-balancing properties of an AVL tree with an order traversal of a threaded binary search tree. Not only do they use the standard left and right child pointers, but also nodes in a threaded AVL tree contain threads which point to the in-order predecessor or successor of nodes when a child pointer would be null. This is an example right here. I used the struct because class would be too long to put in the presentation, but like I said, I will make a part 4 to this video, which will be most likely the last video of this series, just so I could show you guys the code for these. So next is the persistent AVL tree. So these trees allow access to all previous versions of the trees after they were already modified. This is done by sharing common parts of the tree structure between the versions and only having a new node created for the modified path. It uses copy on write and shared subtrees for efficient memory reuse. And this is very powerful for version control of the data structures, which is really good for the program, and it is used in databases and simulations that need snapshots. Now let's go on to AVL plus hash hybrid trees, also known as hashed AVL or indexed AVL. They maintain nodes in a sorted order by using range queries. They are used for fast lookup of hash tables and also are used in systems that need both sorted traversal and constant time access. And the hash map points directly to tree nodes, which gives it order 1 average time lookup, which is very good. And lastly, our last example is the Cache Friendly AVL Trees, variant of standard AVL trees that improve the design and performance of minimizing cache misses. They have an optimized memory layout rather than using traditional node pointer structures, and they use cache oblivious algorithms to perform better for any memory hierarchy without needing to know specifics of the cache. And they also use techniques to improve cache locally, which is so the program can locality, which is so the program can access memory locations that are close to each other. So thank you guys for watching, and that's part 3 of the video. Like I said, for part 4, I'll be going over a code review over these 4 advanced variants of the AVL trees: the threaded AVL trees, persistent AVL trees, AVL plus hash hybrid trees, and cache friendly AVL trees. So if you want to see how those are used, I'll be writing code for that in a Linux environment, and I'll post that up by next week. Thank you guys, and have a great day.